Hi, I'm Norman Wildberger. Today we're going to look at the most important theorem in hyperbolic geometry, which is, of course, Pythagoras' theorem. Or rather, the hyperbolic version of Pythagoras' theorem, because it's a different Pythagoras' theorem from the one that we learn in Euclidean geometry. Along the way today, we're going to review some basic interpretations of our fundamental notion of quadrants. So let me remind you of what we did in the last video. We started with the definition of a point as a triple of numbers in square brackets, the definition of a line as a triple of numbers in round brackets. We have a notion of incidence between the point and the line, precisely when this fundamental relation is satisfied. L times x plus m times y minus n times z equals 0. We also have a notion of duality between points and lines. So if there's a point, its dual is the line just obtained by swapping the square brackets from the round brackets. And similarly, if we start off with a line, then its dual is the point obtained by just swapping the round brackets for square brackets. And here's our definition of quadrants now. Quadrants between 2 points. It's 1 minus this expression, x1, x2 plus y1, y2 minus z1, z2 all squared in the numerator, and x1 squared plus y1 squared minus z1 squared times x2 squared plus y2 squared minus z2 squared in the denominator. So actually we have already seen this expression in an earlier video in this series. Because I may remind you that we originally talked about the quadrants between 2 points in terms of a cross ratio of 4 certain points. So given a point A1 and another point A2, then there are 2 other points naturally associated with them that also lie on the line joining them. What are those points? Well, you take the point A1 and you look at its dual line, the polar according to Apollonius, and that line meets this line through A1, A2 in some point B1. Similarly, the dual line of A2, which is this one here, meets our given line A1, A2 in a new point B2. So we have these 4 points actually, A1, A2, B1, B2, and this cross ratio A1 to B2 and this cross ratio A1B2 to A2B1 was how we originally defined the quadrants between the 2 points. And then we proved, in fact, that in coordinates the quadrants had that particular form. Now, are we allowed to have 2 different definitions for a concept? No, actually we're not. We've got to choose which one of these we consider primary. We know they're both really the same. But now we're going to change our orientation and we're going to make this one our primary definition. Why? Well, this is much more in keeping with most students' familiarity in mathematics. Unfortunately, projective geometry these days is a sadly neglected subject. I hope that's going to change in the decades to come, but currently a lot of people don't know about cross ratios. They don't know even about fundamental things about projective geometry. So starting with the cross ratio is a little bit problematic. On top of that, the cross ratio is actually quite a subtle, of course very important, but subtle invariant, and it's not entirely easy to get one's fingers completely on it. This is completely unambiguous. It's in keeping with linear algebra because there's really some dot products or quadratic forms that are naturally floating around there. It's something that's quite familiar looking to most undergraduate mathematics. And we saw, of course, that it's very much in the same spirit as the spread between 2 lines, our formula for that in Euclidean geometry. Of course, if I had started this course by just starting here and then going down here, I could have done that, but then you would have looked at this and said, well, what does that mean? It would be a kind of a meaningless formula to you. But I could have done that actually. And in a strictly logical derivation of the subject, or strictly logical laying out of the subject, that's maybe not a bad way of proceeding. Okay, so for those of you who have just joined us with this last video, let me say a little bit about this kind of picture. Where does a planar picture like this come from just this kind of triple of numbers orientation? There's something to be explained here. Let's have a look and remind you of some basic things. There are, in fact, many different ways of visualizing or interpreting a triple of numbers forming a proportion. But the preferred way that I want you to think about it is in terms of lines through the origin in a three-dimensional space. So here's a two-dimensional representation of a three-dimensional space with an x-axis coming out, a y-axis in the plane of the board, a z-axis in the plane of the board also. And if we have a point, say the point 1, 2, 3, it means that we're going to go 1 unit in the x direction, 2 units in the y direction, and 3 units in the z direction. And we can visualize that actually quite concretely by thinking about a parallelepiped, or a box, whose sides are parallel to the natural planes of these axes, and whose sides are parallel to the axes themselves. So this little red box that I've drawn here, okay, that one there is the box that represents a side of 1 in the x direction, a side of 2 in the y direction, and a side of 3 in the z direction. So that's exactly the point 1, 2, 3 with commas and square brackets, representing a single point in this affine space. Now this point determines a line through the origin. So we can connect this point with the origin. We get that blue line right there. Now that line is determined by this point only up to a scalar. If we multiply all of these three coordinates by any factor, we get another point on the line. So in fact, the line is actually determined by the proportion 1 to 2 to 3. And so we can think of the line as actually being the proportion 1 to 2 to 3, the thing that we're calling a point on the previous slide. Well, that might sound contradictory because it's actually not a point, it's a line. So why are we going to call this line actually a point? Well, to understand that, we have to see how we're going to view all these lines through the origin. We have all these lines through the origin in different directions. And drawing a three-dimensional picture is a bit cumbersome all the time, so we prefer a two-dimensional picture. And we get that by looking at this particular plane, the plane z equals 1, which is a plane in three-dimensional space parallel to the xy plane, but up 1 unit in the z direction. And the point is that most of the lines through the origin will meet this viewing plane, you might think of it as a viewing plane, in a point. So for example, this line that we started with, a line through 1, 2, 3, goes through this plane z equals 1. And we can find that point by just rescaling this point so that the z coordinate becomes 1. So in other words, if we divide by 3, then we get 1/3, 2/3, 1. That now is a point on the line also, but actually lying in the plane z equals 1. So it's really the coordinates 1/3, 2/3 that determine this point in this two-dimensional plane. And then we can take this plane and kind of move it in a standard position so that the x direction and the y direction are now oriented now in the standard way. X direction in that way, y direction in that way. And then our point 1/3, 2/3, 1 is represented now by that simple point 1/3, 2/3 in this sort of standard affine plane. So we've represented a line through the origin now as a point. And that's very nice, except that it doesn't always work. It doesn't work when the original line was actually horizontal. In other words, had 0 as a third component. Algebraically, why that doesn't work is because you can't divide by that third component if it's 0. So it's not the case that all lines are represented by points in this plane, but most of them are. And the ones that aren't, lines that are horizontal, are represented by directions in this plane. So in any case, this is where we get our two-dimensional pictures from. So a point actually does end up being a point in the plane. And then what we're calling a line is actually the picture of a plane through the origin, which turns out to be a line here. All right, so there's a bit of a review of the interpretation, or an interpretation, of a point, a proportion of three numbers. But let me say that it's not the only interpretation. It's possible to give other ways of thinking about what this point means. And later on in the course, I will show you some other alternative pictures that are quite interesting and connect the same hyperbolic geometry with a different kind of planar two-dimensional geometry. But for now, we're going to stick with this picture. So if we're going to visualize points in the plane, as we like to do, a natural question is, what does the quadrants look like when we think about it in terms of planar x and y coordinates? So for example, let's consider this point A1 that we've just been looking at, the point A1, whose official coordinates are 1 to 2 to 3, but which can now be sort of identified with a point in the plane with coordinates 1/3 and 2/3. And let's choose another point, say the point A2, whose official coordinates are 1 to -1 to 2. If we divide by 2, we get 1/2 minus 1/2, giving us the point 1/2 minus 1/2 down here. Okay, there's the line joining them. The quadrants between them will be denoted by a little number q, and will usually associated with a little rectangle on the line segment joining A1 and A2. And what is it? Well, here's the formula. We have to take these two coordinates, this triple and this triple, and apply the formula, which is what? 1 minus. Now in the numerator we have 1 times 1 plus 2 times -2 minus 3 times 2. So altogether 1 minus 2 minus 6 all squared. To remember to square that expression. And on the bottom we have 1 squared plus 2 squared minus 3 squared, so 1 plus 4 minus 9, times 1 squared plus minus 1 squared minus 2 squared, so 1 plus 1 minus 4. So that's 1 minus 49 over 8, which is minus 41 over 8. That's the quadrants between these 2 points in the hyperbolic plane. Okay, it's going to take us a little while to get used to what this quadrants looks like. So here are some examples, using Geometry Sketchpad, of different quadrants in the plane. So let's write down the general formula for 2 points in a kind of a planar representation. So in other words, suppose that we've normalized so that the z coordinate is 1. So we're really thinking about a point in the standard plane with x and y coordinates x1 and y1. And another point, A2, with coordinates x2 and y2. Then here is just the formula for the quadrants in this special case. It's just the usual one, except that the z1, z2 terms, the z1 squared and z2 squared terms, those are all replaced with minus 1. And now it becomes kind of clear that there's something happening when our point lies on the unit circle. So we can see geometrically that the unit circle is playing a special role here, because that's where this denominator is 0. The quadrants is not always defined. If the point is a so-called null point, in other words, if the x-coordinate squared plus the y-coordinate squared minus the z-coordinate squared is 0, then the quadrants involving that point is necessarily undefined. So our convention is this zero denominator convention, which is that a zero in the denominator of a fraction makes the equation, or the statement in which that fraction is involved, an empty statement. It means we don't have to purposefully exclude that possibility. We can allow that possibility, and if a zero appears in the denominator, it just means that all bets are off and the statement is no longer allowed to have any value or any meaning. So let's have a look now at an example where one of these points is a special point, the point that in coordinates is 0, 0. So A1 will be 0 to 0 to 1. And A2, well, it can be an arbitrary point in the plane, x to y to 1. Well, in that case, the formula simplifies because, well, this term and this term will be 0. This term and this term will be 0. And this term here will just be x squared plus y squared minus 1. And then when you get that over a common denominator, we get x squared plus y squared over x squared plus y squared minus 1. That's the quadrant's Q that is obtained if one of the points is at the origin. So let me make a little remark here. If the point A2 happens to be very close to A1, so very close to 0, then this quantity in the denominator is pretty close to minus 1. And then what we're getting is just the negative of the Euclidean quadrants, x squared plus y squared, between the 2 points. So for points that are very small, very close together, near the center of the circle, the quadrants, the hyperbolic quadrants, is just the negative, or almost the negative, of the Euclidean quadrants. So now it's time to have a look at Pythagoras' theorem. So Pythagoras' theorem in this hyperbolic version says that if we have 3 distinct points, A1, A2, and A3, and if we consider the quadrants as Q1, Q2, and Q3 defined this way, so that Q1 is the quadrants between A2 and A3, Q2 is the quadrants between A1 and A3, and Q3 is the quadrants between A1 and A2, then if A1, A3 is perpendicular to A2, A3, then Q3 equals Q1 plus Q2 minus the product of Q1 and Q2. That's the most important theorem in hyperbolic geometry. And it's one of the most important theorems in all of mathematics. Let's do an example that allows us to verify this in a special case using the formulas that we got in the previous page. So we'll consider a situation where A1 is a point on the x-axis, x to 0 to 1. So it's actually some point there with an x-coordinate little x. And we'll suppose that A2 is on our y-axis. So it has the form 0 to y to 1 for some y, the usual y-coordinate. And our third point will be the origin, or the center of the circle, 0 to 0 to 1. When I say center of the circle, I'm talking about the center as we see it. Actually, it turns out that hyperbolically, the center doesn't have much significance. All right, so we can write down some of these quadrants. Q1 is the quadrants between A2 and A3, the quadrants between this point and this point. Well, that's just a special case of what we did on the previous slide. So it's going to be 0 squared plus y squared divided by 0 squared plus y squared minus 1. So y squared divided by y squared minus 1. And similarly, Q2 is going to be x squared divided by x squared minus 1. Well, what about Q3, the quadrants between A1 and A2? So here we should use the formula, which is 1 minus, okay, we now take x times 0 plus 0 times 1 minus 1 times 1 all squared. So that's minus 1 squared. That's a 1 in the numerator. The denominator is x squared plus 0 squared minus 1 squared, so that's x squared minus 1, times 0 squared plus y squared minus 1, so that's y squared minus 1. So what's the relationship between this q1, this q2, and this q3? Well, it's simpler in this case if we think about 1 minus q3, 1 minus q1, and 1 minus q2. Because 1 minus q3 here is just exactly this expression, 1 over x squared minus 1, y squared minus 1. Now what is 1 minus q1? Well, you're going to get 1 minus this thing. So you over common denominator, y squared minus 1 minus y squared. So it's minus 1 over y squared minus 1. And 1 minus this is minus 1 over x squared minus 1. So if you multiply 1 minus this with 1 minus this, you're going to get exactly 1 over x squared minus 1 times y squared minus 1. In other words, 1 minus q3. And as that exercise that I gave you at the end of the last video shows, this expression is exactly equivalent to Pythagoras' theorem. Let's just check that. If we expand the right-hand side, we get 1 minus q1 minus q2 plus q1 q2. And then the 1's on both sides cancel. And if you bring the q3 on one side and all the other stuff on the other side, then you get q3 on one side and q1 plus q2 minus q1 q2 on the other side. So it's very easy to see that these things are equivalent. So for this particular triangle, and it's actually not such a particular triangle because there is some flexibility. This point A1 can be anywhere along here. The point Y can be anywhere along there. We always have a right triangle because these two lines are perpendicular always. How do we know that? Well, what is the dual of this point, of this line? The dual of this line, because it goes through the center of the circle, is the point at infinity in that direction. And so this line, which is perpendicular in the usual sense, is actually perpendicular in the hyperbolic sense. But you could also check that by computing the equation of this line, and checking perpendicularity directly. So let me give you that as an exercise. So exercise 22.1, show that the lines of the previous example are in fact these ones. There's L1, the line 1 to 0 to 0. The line L2 is 0 to 1 to 0. And the line L3 is y to x to xy. And then use the formula for the spreads between lines to compute that S1 is this expression, that S2 is this expression, and that in fact S3 really is 1. Here's another exercise in the same kind of direction, where we're again choosing one point to be at the origin, another point somewhere on the x-axis, and the third point somewhere directly above that x-axis. In other words, a point that has the same x-coordinate as does A1. So A1 is x0, 1 for some x. A2 is xy to 1, where this x is the same as that x. And A3 is our origin point. Now this is also a right triangle because, again, this line here actually goes through the dual of this line here, which is the point at infinity in that direction. But you can work out all the quadrants and spreads of this triangle using the formulas. Convince yourself that this really is a spread of 1 right here. And you can verify Pythagoras' theorem. Check that it works, no matter what x and y are. So now we come to the moment of truth that you've no doubt been waiting for. The proof of Pythagoras' theorem. Okay, this is one of the major theorems in mathematics. We are going to prove it here. It's kind of curious, in fact, that this is in some sense almost the first publication of this proof. It appears on an archive paper of mine, but the various journals that I submit this kind of thing to are very slow in accepting and publishing these things. So this is a kind of a world premiere right here. Okay, one of the most important theorems in mathematics. In the top 10, for sure. Okay, this theorem. Pythagoras' theorem, with the notation that we already have, this is what we want to prove. The line A1, A3 is perpendicular to the line A2, A3, then Q3 equals Q1 plus Q2 minus Q1 times Q2. Now the proof is not entirely straightforward. So what are we going to try to do? We're going to start by introducing coordinates for these 3 points that we're looking at. It's all about 3 points. So let's be specific and let those 3 points have specific coordinates so we have something to work with. So we're going to suppose that A1 is x1 to y1 to z1, A2 is x2 to y2 to z2, and A3 is x3 to y3 to z3. Well, this statement here is something about the lines joining those points. So we need to know what A1, A3 is. We need to know what A2, A3 is. And here are those things from the join of points theorem. If we join A1 with A3, then here is essentially the J function, okay, applied to these coordinates and these coordinates. That thing, that thing, that thing. In the same way, here's A2, A3, the J function applied to this triple and to this triple. Now, when are such lines perpendicular? Well, remember, perpendicularity of lines was the spread equals 1, or algebraically it was that this times this plus this times this minus this times this should equal 0. And I've just written that out right there. Okay, this times this plus this times this minus this times this equals 0. Now, here's where the remarkable aspect occurs. Okay, so a small miracle occurs, perhaps, in that this thing here, this equation, is exactly equivalent to this one here. In fact, what's along this line here is exactly the same as what's up here, except that everything has been multiplied by a minus 1. This is an identity. The identity is that this thing here equals minus all of this. And how do you check that? Well, you just check it by expanding. So you expand this out, you expand all this out with a minus sign, and then you see that everything here is exactly equal to something there. There's an exact balancing of all the terms. This is x3 squared plus y3 squared minus z3 squared. Here's x1, x2 plus y1, y2 minus z1, z2. And here's the similar product as this one, two of them, x2, x3 plus y2, y3 minus z2, z3, and x1, x3 plus y1, y3 minus z1, z3. Okay, so great exercise. Verify that if you expand this thing out, multiply everything by minus 1, then you can rearrange that to give this. So the assumption that A1, A3 is perpendicular to A2, A3 amounts to the assumption that this times this minus this times this equals 0. And we're going to call that equation star. So we want to prove that if star is true, then Q3 equals Q1 plus Q2 minus Q1 times Q2. So we're going to have a look at these Q's and see how does Q relate to this star. All right, so here now is again what we have to prove. We're assuming A1, A3 is perpendicular to A2, A3, and we need to prove that Q3 equals Q1 plus Q2 minus Q1, Q2. Or equivalently, that 1 minus Q3 equals 1 minus Q1 times 1 minus Q2. Or equivalently, that the difference between 1 minus Q3 and the product 1 minus Q1 times 1 minus Q2 is 0. So let's look at 1 minus Q3, and at 1 minus Q1, and 1 minus Q2. There is 1 minus Q3. It's in terms of the coordinates of A1 and A2, x1, x2 plus y1, y2 minus z1, z2 all squared, x1 squared plus y1 squared minus z1 squared, x2 squared plus y2 squared minus z2 squared. That's immediately coming from the definition of the quadrants. And we have to subtract 1 minus q1. There it is right there. It's exactly the same kind of thing, but it involves the variables for a2 and a3 instead. And we have to multiply by 1 minus q2, which is right here. Exactly the same kind of thing involving the variables for a1 and a3. So this minus this times this. We want to get everything over a common denominator. Here there's these x's 1 squareds and so on, x2 squareds. Here's x2 squareds, x3 squareds, x1 squareds, and x3 squareds. All of these multiplying together. So we're going to take this product of these four things to be the common denominator. So there's an x1 squared and so on there, an x2 squared and so on there, and the x3 squareds and so on occur twice. So there'll be that term squared as the common denominator. Okay, to get it over a common denominator, it means we have to multiply this thing here by the x3 squared plus y3 squared minus z3 squared, this term here, all squared. That's what we're going to do. So we're multiplying this numerator right here by that factor there that's appearing in the denominator here. And here we're just repeating the numerators that are already there. This is the same as that. This is the same as that. So here's 1 minus q3 minus 1 minus q1 times 1 minus q2 written over a common denominator. We would like to show that's 0 if star is satisfied. Okay, we look at this and say, well, when is this 0? Well, notice the numerator is a difference of squares. This is squared, that's squared, that's squared, that's squared. So this is something squared minus something squared. Like a squared minus b squared. And the main thing about a squared minus b squared is that it factors as a minus b times a plus b. So this numerator is a difference of squares, and one of the factors is this times this minus this times this. The other one is this times this plus this times this. And the first one of those things that I said is exactly our expression star. So this times this without the squares, so just that term times that term, minus this term times this term, is exactly what I wrote down on the previous slide. That was the expression star. And we said that if the lines were perpendicular, then star was 0. So if star is 0, then that's a factor of the numerator. That means this whole expression is 0. And so 1 minus q3 equals 1 minus q1 times 1 minus q2, which is equivalent to Pythagoras. That's a proof. Please make sure you understand this proof. It's the main theorem. It's got some algebraic subtlety. All the algebraic subtlety occurred on the previous slide when I changed one long expression to another one and claimed that they were actually equal. So make sure you check that. Make sure that I'm not fibbing. There's one more thing to say about this, which is very important. The converse does not follow. So it's not true that from the argument we can say that if this is satisfied, then the things are perpendicular, the lines are perpendicular, because it could be that the second factor, when we factor this difference of squares, it could be that that second factor is 0. Right? You have a product, one factor times another factor. If we know that's 0, we can conclude that either this factor is 0 or the other factor is 0. But it's not so easy to exclude that possibility of the second factor being 0. So we can't immediately deduce the converse result. Pythagoras' theorem, so far at least, only goes in one direction. If the lines are perpendicular, then q3 equals q1 plus q2 minus q1 times q2. So a few exercises to play around with Pythagoras' theorem. The first is that if we consider this particular triangle with one point x to 0 to 1, another one 1 to 0 to 0, another 1 to y to 0, where x and y are pretty well arbitrary, then I ask you to calculate the quadrances and spreads and verify Pythagoras' theorem. So show that that's a right triangle. And here the same thing for this triangle, where we have three different kinds of points. the point x to 1 minus x to 1, the point y to 1 minus y to 1, and the point 1 to 1 to 1. And this one here, C1 is x to 0 to 1, y is, C2 is y to 0 to 1, and C3 is 0 to 1 to 0. So that's good. We've established the most important theorem in the subject. Next time we're going to talk about the second important theorem, the triple quad formula, which we've seen already in rational trigonometry. It looks a lot like the triple spread formula in Euclidean case. And we're going to explain why that is. It's not just a coincidence. And we're going to have a go at proving that formula too. So I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.